Thanks a lot for the introduction. So actually, I can probably skip these slides, or almost. So let me just add that it's not only the work of me and Avinash, but there are other co-authors and also 2 students that helped a lot for the development. And this is a work that would not have been possible without this project financing the PhD of Avinash. So, said that, the agenda. So I will, can you hear me? When I move my, okay. I will introduce what multi-party web applications are, what is logical vulnerabilities in this multi-party, and then what is the problem that we try to solve. And then Avinash will go into the interesting part, so with the solution that we try to put in place, the results we got, a demo, hopefully. And then it will be back to me showing a bit the industrial side of this work, some limitation and future work. Okay, so what multi-party web applications are? Well, in its general definition, is a service provider web application that provides a service to the user, but in doing that, relies on a trusted third party. So here you have a few examples, single sign-on, for instance, where you have a user that wants to consume a service. Here is Gmail. And in order to be authenticated, the user will be redirected to an identity provider. In this case, it's the University of Genoa identity provider. And if everything goes fine, the user will finally get access to his email. And another classical example is cashier as a service. So in here, you have the users that wants to buy a product on this shopping online. And to finalize the payment, perhaps it is redirected to a payment service like PayPal. So these probably are things that all of us experience every day, right? And are pretty popular scenarios in nowadays web applications. So here you have some numbers. And these numbers are getting higher and higher. So just to provide some more concreteness, let's see a bit more details about one of these scenarios. So here you have Alice that wants to access the Gmail. And it does a login request, and Gmail replies with what is called an authentication request. So with this authentication request, Gmail is asking, I don't know who you are. Please go to the trusted third party, so the user is redirected. And the trusted third party, the user will have to provide his credential, username and password. And once that is done, the trusted third party will issue an authentication assertion that is digitally signed by the trusted third party. In this case, it would be the University of Genoa doing that. And inside the authentication assertion, among other parameters, other things, there will be the identity of Alice and the identifier of the service provider. So basically, you are saying this authentication assertion has been issued by this identity provider for Alice that want to access this service provider. So pretty obvious. And then Alice is redirected back to the service provider if everything goes fine. If the assertion is validated somehow by the service provider, Alice will get access to the email. So a pretty common scenario. However, on this scenario, many vulnerabilities have been reported over the years. And many of these vulnerabilities are what we call logical vulnerabilities. So what is a logical vulnerabilities? Well, basically, it's an incorrect logic of the design implementation of the protocol underlining the scenario. So this could be, you just do not bind properly 2 parameters of the protocol, and therefore the attacker can do something nasty. Here you can see an example. This attack was discovered in 2008 and was for the SAML-based single sign-on of Google applications. And basically what is happening is that the trusted third party that is deployed in Genoa, but was the trusted third party provided by Google, so it was just a deployment that was done there, was not having the service provider field inside the authentication assertion. So now you can already imagine what can get wrong. So if we see an exploitation of this, we have Alice, that here is the victim. So we identify the victim as UV, and is playing the protocol with here a compromised service provider. So a service provider that got compromised by an attacker, right? And at some point, he will just play the protocol, and what the attacker will do, we start another session This time is not, this previous session was between the victim and this service provider M that we call service provider malicious to indicate that it is compromised by the attacker. And then the attacker will start another session here. This time is himself playing with the target service provider, for instance, Gmail. It's just a man in the middle here, what you have. And so he will do the login request, and then he will just replay the assertion that he got here. And since the assertion doesn't contain the service provider for which it was originally issued, well, what happened is that the malicious guy gets authenticated in Gmail as the Alice victim. So this is just a strategy, and if you try to formalize it a little bit, it's just a replay attack. A replay attack that concerned the authentication assertion that was issued for the victim while playing with this service provider malicious, and we are just replaying it in another session where the malicious guy is playing with the target service provider. Okay? So it's a replay attack. And there are many other attacks of this kind. So here you see an excerpt. You see some, let's say, reference. At the end of the slides, you can find the papers where these attacks were discovered. And are on different scenarios, single sign-on, but also payment. So our idea was, can we try to elaborate a technique such that we can, that is viable, and we can discover this kind of attacks in a kind of scenario-agnostic way? Because the previous attacks that were reported were always discovered with the different techniques. Here and there, something that was specialized for a specific scenario, something that was specialized for single sign-on or for payment, etc. So can we try to find an approach that is easy to be used, at the same time able to discover these kind of things? And with that, I leave the floor to Avinash that will go into the solution.
Okay. Thank you, Luca. So when we started with the attacks that have been reported in the attacks that have been caused by logical vulnerabilities, we had certain observations. Now let's look at some of them. So our first observation that the strategy that was used behind many of these attacks are the same. So it's probably difficult to see from here, but let's focus on the attack strategy. So if we formalize the attack strategy, you can see that, so this is the attack that we saw just now in Google. So replay the authentication assertion from this type of session in this type of session. So this attack was discovered in 2008, and in 2013, another researcher, through formal verification, found an attack in Facebook, in service providers integrating the Facebook single sign-on solution. And basically, if you look at the attack strategy, it's still the same. Just instead of the authentication assertion, he replayed the access token. So imagine when this attack was discovered, and if we had captured this attack strategy in some form, and then if this attack strategy was applied to Facebook single sign-on, then we would have identified this attack without using formal verification or without going through the complexity of formal verification. So this is not just a special case, because we were also able to see that different techniques that have been used to identify attacks in different solutions, if you look at the strategy, they're basically the same. So further examples. So another question is, can we exploit the similarity in attack strategy to discover like new attacks in an automatic way? So this is a question. And another observation is, okay, let's say we somehow captured this attack strategy, and we have a new application we want to test. On which elements are we going to apply this attack strategy? So as you know, all these protocols are based on HTTP protocol. And in HTTP protocol, there are a lot of elements like cookies, referrer header, and a lot of parameters in the cookies. So if we want to, the ideal case is we can apply attack strategy in all these elements. But can we do it in a smarter way? So then we looked at the security critical elements in the protocol and their properties in the HTTP traffic. For instance, another researcher has pointed out that the uniqueness of each HTTP element is a very interesting concept. So we look through that angle. For instance, let's take the case of the login request. user is sending his username and password to the trusted third party. So it contains the username and password. And this is a security critical parameter. And these are user unique. So another user executing the same protocol will have different values. But for the same user, it's going to have always the same values. And then another interesting concept is session uniqueness. So this authentication request and the authentication assertion, these are very important security critical parameters. Their value changes in each session. Then another question that can come to your mind is, okay, but the cookie is also session unique. So if we apply the attack on cookies, it's not going to work. So we need something more than these uniqueness properties. So for that, we identify another interesting property which is related to the data flow property of these security critical elements. For instance, if you look at this, this security critical element, it is flowing from the service provider to the trusted third party. If you look at the traffic, we can see that. Similarly, if you look at the authentication assertion, we'll see that it is flowing from the trusted third party to the service provider. So now we know that it is possible that we can understand from the HTTP traffic of the underlying protocol which attack strategy we can apply. Now the third observation. Okay, so we have an attack strategy, we have a protocol under test, and we know which are the interesting elements in which we can apply the attack strategy. So now after applying the attack strategy, we should know whether the attack worked. So one option is either we can ask the tester, okay, did the attack work? I tried this. But if there are 100 attack strategies, we cannot always bother the tester. So can we somehow automatically determine whether the applied attack strategy was successful? So to answer this question, so this is the attack that we saw earlier. So when the authentication assertion was replayed, when the attack worked, the service provider or the trusted service provider replied with welcome Alice message. So this message or this pattern will be returned in a proper session between Alice and the service provider. So when this was replayed, it returned this pattern. So if we extend the attack strategy, so we can extend this attack strategy considering this what we call as the flag of a session. So replay this authentication assertion in this session and get this flag. So this is now the strategy that we can use to not only perform the attack, but also check whether the attack was really successful. So as I said, this pattern, it can be directly in the HTTP traffic, or it can be something in the DOM, which is like executed by a JavaScript and which is like displayed in the DOM. Now, another observation that we made was most of the attacks that were reported in the past were considering the threat model in which the attacker can play the role of a malicious user or that of a malicious service provider. And in order to execute all these attacks, the attacks that we considered, we just need 4 nominal sessions. So the victim user is executing the protocol with a benign service provider. The attacker is executing the protocol with the benign service provider. Similarly, these 2 users executing the protocol with the malicious service provider or a different service provider. So if we have this HTTP traffic from these 4 sessions, we can basically reproduce these attacks. So another question is, they considered these threat model. Now, what if we consider the threat model in which the user, malicious benign user, and the malicious user shares the same browser? That's what we call the browser history attacker threat model. So in this, we don't consider the case that the user does not log out from the session. So he logs out from his session, but he does not clear the browser history. So the attacker can see the history of the victim. So this threat model was considered in this while analyzing multi-party web applications. So we thought, okay, let's consider this scenario and see what happens. So now that we have all the attacks, we found that many attacks have similarities. So how can we convert all our observations into something called attack patterns? So let's focus on these 2 attacks, the attack in Google and Facebook service provider. So let's formalize them. So in both these attacks, 2 different elements were replayed. So if we generalize them, let's call it a fancy name. Let's call it replay attack 1. So the strategy is replay an element X from this type of session in this type of session. So what should be the property of this element X? So this element X should flow from the trusted third party to the service provider, and this element should be session unique or user unique. So if we focus on these elements in the protocol and perform this attack strategy, and we get a flag which belongs to that of this session, for example, welcome Alice, then we have an attack. So this is how we convert these concrete attacks into attack patterns. We continued this exercise for a lot of different attacks. For instance, this is the attack that we saw just now. Sometimes attacks can be really complicated. For instance, we don't have to get into the details, but if you see the attack strategy, let's start from the bottom up. There is a replay attack to get an element Y, and that element Y is replayed in another session. So there is a nested replay, and these are the conditions. So these are inspired from different attacks that have been reported in the past. So these attacks were inspired from previous attacks, but this is the attack that we modeled by considering the browser history attacker. So now let's go to our approach. Our approach consists of two phases. The first phase you already saw. We acted as security experts, surveying attacks from the literature, identifying similarities, and creating attack patterns. We can also consider new threat models and create attack patterns. Now there is somebody who is like a tester who has a multi-party web application to test. So he is basically applying these attack patterns to detect attacks. So what he should do, he should provide what we call configuration and recording to, so what we offer is a security testing framework. So to our framework, he should provide a configuration. And what should be this configuration? This configuration is basically, he should provide an implementation of the solution. And then he should provide what we call the user actions to belonging to the 4 different nominal sessions. So basically by executing these user actions, we are reproducing these 4 different types of sessions. So once this input is given to our security testing framework, we automatically perform what we call inference. So in this inference, we execute the protocol, we identify what are the security critical elements, we identify their properties, and then in the next step, what we do is we apply these attack patterns. So we check the precondition, apply the attack strategy, and check whether the attack strategy was successful. And then if it was successful, we report it to the tester, and the tester can check whether the attack is indeed true. So this is architecture of our implementation, and we are proud to say that we used OWASP SAP for our implementation. So this is our implementation of the inference and the attack pattern engine. Basically, our attack pattern, our testing engine depends on OWASP SAP to collect HTTP traffic, to execute user actions, and to manipulate the traffic like an attacker and send it to the multi-party web application under test. So now that we have a security framework, and we used our security framework to analyze different real-world applications, and we had some interesting results. So first of all, since we considered the browser history attacker threat model, we discovered 2 attacks in, for instance, let's take this attack in developer.linkedin.com, in which we found out that even after a user logs out, there are some values in the browser history, for instance, the member ID parameter, and the attacker just needs these 2 information in order to log in as the victim. Similarly, some attacks that were reported in single sign-on, we created attack patterns from them. We applied to the payment scenario, and we discovered new attacks. Not only in payment scenario, but also in other scenarios like the registration via email. Similarly, we found interesting attacks in prominent applications like Pinterest.com, and these attacks that we applied were inspired from totally different single sign-on protocols. And for most of them, we received acknowledgements, and for some of them, we did not receive acknowledgement. We have anonymized their names. And an attack was reported in OS Commerce to checkout integration. we create an attack pattern, and we found the same attack in the latest version of OpenCart just by using our tool. And with all these results, we published a paper in this year's NDS symposium that happened in February. And now let's see a demo of our tool. So in this demo, what we'll be seeing is the cashier as a service scenario, the payment checkout scenario. We'll be testing the latest version of OS Commerce. I believe up to yesterday, this was the latest version. And what we'll be testing is the two checkout is like a payment service provider. So we'll be testing this scenario. So as I said earlier, the tester should provide the configuration and recording to our testing framework. So let's switch to our tool. So this is the UI of our tool. We have some issues with the resolution, but I think it should be fine. So he wants to create a new test. So he creates a new test. And as I said, he should provide user actions and flags. So how can he provide these user actions? There are a lot of technologies available to tackle this scenario. So this is the application that we want to test, which is OS Commerce. So he can use something like the Selenium plugin in order to record the user action. For instance, he can, whatever actions he performs will be recorded by the plugin. We enhanced it to support, to make it more robust. So let's say he starts like, and he signs in, and then adds a product, and then continues to checkout. And he selects to checkout as the payment service provider. And basically, he will be redirected to the payment service provider. As you can see, all the actions that he performs is recorded here. And he just provides he submits the payment. And the shopping was successful, so he can use this string in order to, as a indicator, to say that this string can be used in order to say that the protocol is successfully executed. So after recording these user actions, basically he uploads user actions corresponding to each of these sessions. And then he will have to provide the flag that he identified, like it has been processed. So we don't have the time to run the whole test because it takes like 40 minutes. So I will show you a report of what will happen if he uploads the user actions and runs the test. So what will happen after he provides the configuration and recording is our tool performs the inference and identifies the properties of the security critical elements. So I'm taking an already run test, and this is the result of the inference. As you can see, it has automatically identified a lot of interesting elements and the properties of these elements, such as some of them are like user unique, and it flows from the service provider to the trusted third party, and also the trusted third party to the service provider, where is this element located, which is the URL of this element, etc. And then after inference, it applies each attack patterns and reports the attack. So let's see an attack report. So it says, the tool says it applied 4 different attack strategies, and it found an attack for RI3. So what is RI3? So just to recap, RI3 is execute the protocol, get an element, and reuse it in another session. So in the context of OS Commerce, it is purchase a product, get some elements, payment tokens, replay it in a new payment purchase, and you can reach the end. That means you can pay once and shop multiple times. So in this case, it tried different combinations. It tried to replay different elements, and this was the combination. So the elements key and order from one session can be replayed in another payment session, and he can buy products for free. So this information, we believe, is sufficient for the attacker, for the tester to reproduce the attack and verify that the attack is not a false positive. And also the input from the output of the inference is really sufficient to create new attacks because he knows the details of the security critical parameters. So with that, I move the session to Luca.
Okay, thanks. Thanks, Avinash. Yeah, time is running out, actually, so let's quickly look at the industrial side. So basically, we are using this tool at SAP at the moment, this prototype, actually, because it's a research prototype. And we have done some pilots with a few business units. And one of these is we have an e-commerce solution on the cloud. It's called SAP Hybris e-commerce. And that was successful, but I mean, we are still evaluating whether indeed in the company we have many of these scenarios and what we can do with this tool. And one of the things we are working on is for sure improving the usability. So the interface that you just saw was released, I think,
today morning.
2 days ago. So, and it's still, you know, you need to create all the management that is around, etc. So usability is for sure something we have to work on. Concerning the availability of the prototype, so at the moment it's available at SAP only. So, however, I mean, and we are still discussing what should be the delivery model for the prototype. If one of the options is to give it as open source. So, in case you have a scenario and that fits this multi-party case, and you would like to validate, well, reach out to us, and we can see what we can do. For what concerns limitation and future direction, I mean, what you have seen is a set of strategies that we put in place. The nice thing is that we know exactly what we are testing and what we are not testing. However, we don't, I mean, claiming full coverage would be not possible, right? So, as many other approaches, is not complete. However, there is some research question that might be interesting. So, can we reach full coverage for replay attacks? I mean, replay attacks, in principle, naively, I could just start replaying everything, right? And waiting. At some point, it will finish, and it will tell me, I was trying to replay this, and that, and didn't find anything. So in principle, you could do that. It's probably not viable as solution. So the interesting question would be, can you reach full coverage for replay attacks in a viable manner? And this is something we like to investigate a bit more. Another thing is observability. So what you have seen is that our tool acts as a proxy on the client side. So we can just observe what is happening between the two entities, so the service provider and the trusted third party on the client side. So if there is any back-end communication between the service provider and the identity provider, we will not see that, right? And there are protocols, I mean, there was an interesting presentation just before about OpenID Connect. There are protocols where indeed that happens. So it might be important also to work on this. So for instance, to put a proxy on the server side also, and to see, and to be able to combine these two sources of information for the inference and for the application of the strategy. So in conclusion, yeah, we have identified 7 attack patterns. We have a prototype for black box security testing of this logical flow. Oh, we have still 10 minutes. Okay. Well, then we have a lot of time for questions. It's based on OWASP, and we were able to discover quite a number of new unknown vulnerabilities. If you are interested in the technical details, read through the paper, reach out to us. We are here for the entire conference, so it will be a pleasure to talk with you. And yeah, industrial exploitation is ongoing. Thanks a lot.
Any questions? Wait. You shall wait. As you're heading out, there are red and green cards at the back. Please put one into the bucket to let us know what you think of the talk. Thank you.
So I'd like to ask, is your tool publicly available?
Yeah, well, it's what I tried to say before. At the moment, it's only available at SAP, so our company. However, if you have a scenario that you would like to validate, reach out to us, approach us, and we can see what we can do. Okay?
Questions?
Are your attack patterns publicly available?
Well, the attack patterns are available, right? Are written in the paper. So in our case, we're Python scripts, so you can just re-implement. However, I mean, I must say that we patented the solution, so the intellectual property is somehow protected. But yeah, the attack patterns are publicly available, so they are not hidden.
Cool, thanks.
Questions?
Yeah, I have one question. What of the 21 unknown vulnerabilities did you found? What are these kind of vulnerabilities in the single sign-on protocol?
Just to give you a few ideas, something interesting that we found was in the Stripe checkout protocol. So we found out that you pay to at an online shop without providing your credit card details, and the shop just gets a token. It is possible for a malicious shop to get a token belonging to you and use the token to go to like Tesla.com and buy a car with your details. So you don't provide your credit card details to the shop directly, but still the shop is able to purchase things from your card through the trusted third party. And then another thing we found in Pinterest is if both of us are in the same network, then Pinterest is protected with HTTPS, but still somehow I can manage to get your access token by monitoring the traffic. It's not so straightforward like directly checking your login session. It's like I have to send you a URL. If you click on it, your access token will be exposed to the network, and I can use that to log in as you in Pinterest. So these are some of the examples. You can read the paper for more details.
Any more questions? I have one, if I may. The emerging identity access management protocols, legacy SAML, OAuth, and OIDC, they all encourage you to put heavily sensitive data in a URI. Yet the secure coding guidelines usually say never put sensitive data in a URI, even over HTTPS, because they leak all over the place. Browser history, refers, the server logs. So do you think this is a fundamental problem with all these next generation protocols? And is there anything we can do about it? Again, my concern is we're putting access tokens that bear access tokens that by themselves provide major access and similar in URIs, which seems crazy to me. Any thoughts on that?
We can enforce like restrictions like don't send it to the URI, send it as like post message, etc. But these are like nice guidelines that the developer sees, and it's up to him to implement them. So even if we restrict a lot of things, we still have limitations. So these protocols should work in the browser environment. So even in the case of URIs, they provide, okay, when you are sending the access token, use the hash parameter so that it's never sent to the network even though it's present in the URI. But still there are like attacks that can, like using cross-site scripting, you can extract these tokens and all this. So that's how the web is. So you have to live with that.
That was a depressing answer, but any other questions?
So my question is, are you considering to cover more advanced attacks, like, for example, a user shouldn't make a number of orders per day, some constraints of that type, some logic, really advanced rules made by the business?
If I heard you properly, you want to say like whether we can detect like advanced attacks or like how to model them? Advanced logic, it's not.
Yeah, so my question is, could you cover advanced logic rules? Like for example, a user shouldn't make number of orders per day. When a user makes an order, he shouldn't make a mix between two different products of that type, something like that, made by the business. So could you be able to cover something like that? or it depends on the protocol you're.
Yeah, it really depends on the most prominent attacks that were discovered. So we focused on a subset of them. Of course, we could not like target all these attacks, but in future we are like, that's why when we are doing pilots, we'll see more scenarios, and that's why we have the possibility
So
to
you have the flexibility of adding new
Yeah.
scenarios. So
Yes. It's like you just add a new file as an attack pattern, include them, and then you can check for this attack.
More questions? Questions? Gentlemen, thank you so much for such a fantastic talk. Round of applause.